Okay, so we're going to talk a little bit now about correlation and its use in statistics. So sometimes you might have two variables that you've maybe measured, and you might want to know something about the relationship between those two variables. I mean, is there, for instance, even a relationship between them at all? So one of the things, this is an example here where I think they've collected some data from electoral districts in America, and they've looked at the proportion of people who think that global warming is caused by human activities. You see it's kind of ranging from quite low to kind of reasonably high. And then they've compared each of those electoral districts to how much the Democratic candidate got in the presidential election in 2016. And you can see that it looks like there's a relationship here. You have a trend in these data showing that if you think maybe climate is caused by global warming, then it seems to make you more likely to vote for a Democratic candidate. So what we're going to do now is talk a little bit about how we can kind of quantify a relationship between two different variables. So the quantity that we're going to use is this factor called the correlation, and it can be calculated from this hideous looking equation here, and we'll just have a bit of a delve into how this works. But just to point out that you don't have to go through all of the maths in here on your own when you're actually doing these calculations. Quite often statistical packages or programs like Excel have functions that will actually do all of this maths for you. So just have a look at what this equation actually means. So if we have some data we've measured things with x values and y values. And here's an example of 4 data points I might have measured. Now they look like they're in a perfect square here, and that's just to make the explanation a bit simpler. But you can imagine these randomly distributed over the kind of data space. And for each of these variables, for x and for y, we could work out what the average of these data were. So you can see the average of these data in the x value would probably be somewhere around 6, and in y it would be kind of 5. So that would be the average of those data. And if we have a look at what how R is calculated from these data, we look up here. We've got this Greek sigma, and what this means is that we're going to do this maths here for each of the samples, okay, and then we're going to take the results of that calculation, then we're just going to add them up, okay, starting at the first sample, going up to the nth sample. So in this case, it's going to be going from the first to the 4th sample. That's what this little subscript means down here. So the first sample, second sample, third sample, 4th sample. It doesn't matter which order you do them in. And then this little bar above the x, that's the mean value of x and the mean value of y. So for example, if we take this data point here, we could take the value of x minus the mean value of x. The value of x is 8, minus 6 is 2. Up here for y, it's 7 minus 5. So we've got 2 times 2. It's going to equal 4. So the value for that point will be 4. And we're just going to add them up for all of these points here. Okay. So in this case, looking at the top, in this case, we've got a kind of a special case because of the way I've arranged the points. So this value of this point, so the value of x is 4 minus 6. So that's going to be minus 2 times 2 for the change in y. So this case is going to be minus 4. So you can see that actually, if you have data in this kind of quadrant up here, that's going to give you positive numbers. Over here, you're going to get negative numbers. You're going to get negative numbers here. And down here, you're going to be taking a negative number times a negative number, which will give you a positive number. Right, so if we then go on and see, actually, if the data starts to cluster more along a linear relationship like this, you can see that those, I guess previously, that all of this, we had 4, minus 4, minus 4, and 4. If we add all those numbers, they're going to start to cancel each other out. In fact, in this case, they will perfectly cancel out, and the sum at the top would be 0. Now, if we actually take this example here, and where the data are starting to fall more along a linear relationship here, so we could take this again. This is going to be 4. This is going to be 4. But now the data aren't so far away from the mean in this quadrant and this quadrant. So in this case, this is going to be 1. Well, the change in x is going to be 1. The change in y is going to be -1. So that's going to be -1, add -1, -2, and add it to 4 and 4. So that's going to give us a sum at the top here of 6. Okay, so the larger this number at the top is, the more of a relationship we're going to have that goes up and down like this. And if it's going to be a big negative number, we're going to have a relationship that goes up and down like this. Now, the value of this sum at the top really then depends on the values of the numbers on the axes. So to correct for that, what we do is we have this term along the bottom, which just basically normalizes all of the things we're adding up, so that r ends up between 0 and 1. And the way we do that, to avoid kind of adding positive and negative numbers together, we take the square of numbers. Okay, so that if you have a negative number, then you'll end up with a positive answer to this bit. And then once we've added all of those up, we then do the square rooting. Okay, so actually, if you kind of look at this thing on the bottom, we're actually, its magnitude should be the same as the magnitude at the top, because we've got a square root, but then inside that square root we've got squares. So the top and the bottom very similar, except we're on the bottom we're basically getting rid of the fact that adding up positive and negative numbers will start to cancel each other out. Okay, so that means that if we look at what this means in terms of kind of clouds of data, if we have a correlation that's positive, kind of like this, it's a perfect correlation between two variables, our data should fall along a straight line. And if it's a perfect negative correlation, it should also fall on a straight line. We should get an R of 1. If there's absolutely no relationship between one variable and the other, we just have a cloud of data, kind of a shotgun blast like that, we'll have a correlation, an R of 0. Whereas if we've got a kind of an intermediate kind of relationship like this, where it looks like there is some relationship, then we might have a correlation of somewhere in between 1 and 0. I should point out at this point that the actual value of the slope of this relationship, that R is independent of that. Unless the slope is exactly 0, then there is no variance in one of the variables for there to be a correlation with. But it doesn't really matter what the slope of the line is. That is kind of independent of R. It's just how closely defined that slope is. Okay, so we can take this a little step further and make it a little bit more useful. So it turns out that if you take the correlation R and you square it, that gives you a measure of how much of the variance in one variable can be used to describe the variance in another variable. So for example, if we have a correlation of 0.5, if we square that we get 0.25, and that means that then 25% of the variance in one variable can be used to describe the variance in another. So that's not terribly good, but when you have higher correlations, kind of up here, we might have an R squared of maybe 0.8, so 80% of the variance in one variable can explain the change in the other variable. So we'll come on to that in some of the examples later on. But just to be a little bit cautious here, we don't, just by measuring this correlation, we don't know anything about the direction of that correlation. We don't know if one thing causes the other or that thing causes the initial thing. So as an example here, smoking might lead to having lower exam marks. If you could do a survey of how much people smoke, you measure how kind of like clever they are using some kind of exam, you might find that people that smoke do less well in exams. So you might say, well, smoking causes causes stupidity or poor exam performance. But actually, the correlation might work the other way around. So people might be kind of used to not performing so well in exams, and that might lead them to maybe make some poor life decisions and may take up smoking. So we don't know which way around the causation works. There can be in more complexity, so there could be a third thing. There could be a third variable that we're not maybe measuring, and we just measure two variables. They look like they correlate with each other. There could be something else causing that. So an example here, if you go to a primary school and you test some children, see how good they are at reading, and measure how big their feet are, you might find that if you measure all the kids in the primary school, that there's a seemingly good correlation between how big someone's feet are and how good they are at reading. The thing that we're missing here is age. So there's this third variable, age. So older kids tend to have bigger feet and tend to be good at reading skills. So the reading skills and the shoe size not necessarily having anything to do with each other at all. It's just this third variable that maybe links them together. And then finally, there's correlations which just occur by chance. There's no link between them whatsoever. It's just if you have enough random data, then some of it will correlate with something else. So the famous example here is that if you plot up how much piracy there's been through time, and you look at how the planet has warmed, it seems that piracy has declined while the globe has been warming. So maybe it's the absence of pirates that have caused global warming, which is obviously wrong. Okay, so there's this little jokey cartoon at the bottom to kind of illustrate this even further. So there's this kind of students that may be talking thing that hopefully you maybe thought that correlation caused causation, and now you don't think that. And there's this implied link that maybe this kind of relevation down here is due to you attending some kind of stats class, but it just could be by chance. There's no direct link, okay, just by there being the observation that your kind of understanding of statistics has improved, whether that is directly caused by going to the lectures. You could have gained that knowledge some other way. So just to kind of summarize this in a kind of like hideously complex plot here. So if we have two variables, A and B, and we plot those, maybe A on the vertical axis, B on the horizontal axis, and we find some correlation with them. This might have an R of maybe 0.8, something like that. It could be that A is causing B to change, or at least is causing at least 80% of the change in B. Actually, not 80%. It'll be something else. 8 times 0.8. It'll be 60%, 64%. Anyway, because 0.8 squared is 0.64. Anyway, back to the point here. But just because we've got this correlation, the causation could in fact work the other way around. So it could be that B causes A to change, or it could be both. A causes B to change, and then B causes A to change back in turn. So the direction of the causation, okay, is completely unknown if we only do the correlation analysis. You could also have this intermediate variable. So this is an example of for instance, age on shoe size. It could be that there's some variable C, maybe age, which is causing shoe size to increase, and then that is also causing the age is also causing reading skills to go up. And then it might appear that these two, A and B, are related to each other, but in fact it's this mystery secret hidden variable C which is causing the change. And again, just like with this direction, the directions can work the other way around. It could be that A is actually causing C to change, B is causing C to change, and because they're affecting the same thing, then that means that there appears to be a relationship between A and B. Okay, and you can also have kind of like causations that go through loops like this, or as in the case with pirates and global warming, there could be no link at all between A and B. This correlation has just occurred by chance. Okay. So this is some examples about this from the real world. So we've got on this graph at the top here, we've got CO2 concentrations, annual average CO2 concentration in the 60s. The present day, these orange dots increasing through time, and then the average global temperature, which is the grey dots here, also increasing through time. So rather than plot these against time, we could plot them against each other. We could plot the CO2 concentration against the global temperature, and we could see that there is this correlation between the two. So in this case, the R squared is 0.84, so 0.85 actually. So 85 of the variance in CO2 is related to variance in temperature. So we could think, well, actually, CO2 causes global warming. Okay. Now, just from that correlation analysis, we can't actually say that, because it could be that global warming affects CO2. So we don't know which way round these are. And actually, if you warm the planet, you can actually change the CO2 concentration as the carbon dioxide becomes less concentrated in the becomes less soluble, in the ocean. And there are other climate feedbacks can lead to kind of changes in CO2 because of changes in temperature. So this is one of the examples where actually maybe CO2 can cause the globe to warm, but then the globe warming can cause CO2 to increase. And this is just an example to show that. So this is looking at against time. So the present is kind of off the graph over here somewhere. This is the last glacial maximum, about 20,000 years ago. And the blue curve on here is the global average temperature. So in the last glacial, it was colder by about 3.5 degrees colder, and then up in the Holocene, it's kind of just about a little bit cooler than it is today. And then you can see here that the CO2 concentration in yellow seems to rise up kind of in the same way as the temperature of the whole planet, but actually you can see that here the CO2 concentration seems to start rising up before the global temperature change. So in this case, we're able to use the timing of change. So when we plot things against time rather than just each other, we can see here that the CO2 concentration rises before global temperature. So global temperature can be caused by CO2 rise, because the CO2 rise happens first. So one to be the cause, it has to happen before the effect. But actually, if we look a little bit more detail at the temperature, we actually can isolate from the global temperature just Antarctic temperature, and those seem to be going up at the same rate. And in fact, maybe the Antarctic temperature is rising a little bit before the CO2. So in this case, this might be a case where the CO2 actually is coming out of the ocean in the Antarctic because of warming there, and that's causing the initial rise. So just to summarize this, you can see with correlation that there might be a relationship between two variables, but you don't know anything about the direction of those two. So to get the direction, you need to know something about the mechanisms, and you can start to tease apart which thing caused what by using techniques such as seeing which changed first. Another example here, looking at correlation of two variables. So here we've got atmospheric CO2 concentration. Okay, so this is actually plotted on a logarithmic scale here. So this is high CO2, low CO2 over here, but it doesn't increase linearly. And then we've got sea level. Okay, so you can see that there is what looks like a positive correlation. So when sea level is low, we have low atmospheric CO2, and sea level is high, we have high atmospheric CO2. But there is perhaps a missing variable in here that kind of links these two together that we're maybe not seeing. So perhaps it could be that there's a relationship between CO2 on its own. There's no reason why adding CO2 on its own would change sea level, because the sea level doesn't really care about the atmospheric gas composition. It's just the mean level of water. There might be links between sea level and atmospheric CO2. Okay, so there are processes in the carbon cycle which rely on a bit of land being land rather than ocean. So, for instance, the formation of coral reefs. If you raise sea level, you might promote more coral reefs growing, and that will have an effect on atmospheric CO2. Okay, actually, that effect would make it go the other way. So, more coral reef growth more coral reef growth does actually release CO2. So that might explain that. But one thing to note here, that there's a missing variable that we're not seeing here to totally explain the correlation, and that's temperature. So the link between atmospheric CO2 going up, that's changing temperature, which is then having an effect on sea level. So that's kind of this case here, which we might have a kind of a link going from CO2 changing temperature, causing sea level to change. So again, you have to think about what the mechanisms are. Another thing to point out is that actually a thing that we can use here to investigate the processes that are going on is actually the relationship here appears to be different from the relationship kind of up here. So we can look on some of these kind of I guess more criteria that to assess whether there any good correlation that we find, a high R or a strongly negative R. Can we say anything about causation? So we can look at, does A change before B? Look at the timing to work out what caused what. Is the correlation actually higher? So values close to 1 tend to imply more of a causation than values closer to maybe 0.5. Another thing that's quite important in this testing is this dose relationship. So if you have a small change in one variable, does it cause the same change as if you have a large change in one variable? So going back to this kind of, so if you have basically a small change in CO2 here, that appears to have a very large effect on sea level here. Okay, but if we then change CO2 again by maybe the same amount, which on this logarithmic scale will be up here, that doesn't seem to have much of a change on sea level in this portion of the graph. So that change in the sensitivity of the relationship along different values of one of the variables, now that does give us a hint that there is not a direct causation going on. Okay, so consistency, I mean, if you repeat the experiment, you get the same results again. That's a good thing to test against kind of just random data causing there to be correlations which aren't real. But one of the most important ones is, can you come up with a physical basis for a link? Okay, and if we go back to the example here, there are physical bases why CO2, because it's a greenhouse gas, that should cause a change in global temperature. And global temperature should cause there to be a change in CO2 because of the solubility of gases in water being less at high temperatures. So you have to think about not just searching through data to find correlations, but actually thinking about what the physical basis of those correlations would be. And part of that goes towards, could there be another reason for the correlation? Okay, can we try and isolate just changing one variable to kind of remove any uncertainty from these kind of other factors, these kind of C variables? Okay, so there are also these steps which you can go through to investigate a little bit further whether a correlation is a little bit more than just a correlation, but there's actually a causal relationship between the two. So here are some examples. You can kind of, I guess, try and type in those web links if you really must. Just some again, these kind of spurious examples. Fresh lemons imported from the USA to Mexico. That seems to correlate quite well with highway fatalities, so car crashes. So there's quite a strong correlation here between these data. So it's got an R-squared of 97%, or sorry, 0.97. So 97% of the variance in the import of Mexican lemons can explain the change in car crashes. But actually, this has just occurred randomly by chance. If we looked at like a range of other imports from maybe other countries, you might if you picked up enough data, you'd find enough sets of maybe 5 data points that would actually fall on a straight line just by chance. So it just happens that over time, since 1996 to 2000, the USA has been importing more and more lemons for whatever reason. Really like gin and tonics, and over that time, for maybe some other completely unconnected reason, their roads have become slightly safer. Okay, so there's this random chance, and there's also this is another nice example. So this is from the journal, the New England Journal of Medicine, looking at chocolate consumption. So countries that eat lots of chocolates, so UK, we love our chocolates, Germany and Switzerland, and how many Nobel laureates they have, so how many Nobel Prizes are won by that country. And it looks like if you eat lots of chocolate, or at least your country eats lots of chocolate, it looks like you have some kind of higher tendency to produce groundbreaking scientific research or literature. And actually, the journal article actually goes into some detail, actually trying to propose a physical mechanism that actually some of the chemicals in chocolate actually do leads to kind of like more intelligence in their population. But there may be other controlling factors here. So you can see maybe it might just be that chocolate consumption correlates with the richness of countries. So the GDP and the countries that have got lots of disposable income might have more money to spend on higher education and scientific research. That might explain some of these up here. It doesn't explain the USA down here. Uh, um, it might be a completely different. It might just be randomly by chance. Okay, but just to point out that these just because there is a correlation doesn't necessarily mean that there is a causation between these things. And this is kind of another example of this. So if you look at this is, I'm not entirely sure this is real data, but looking throughout the year, data from maybe beaches. We've got amount of ice cream sold and how many shark attacks there are. And this must be fake data, because a shark attacks of 20 per month, that does sound like a ridiculously high amount. So I assume that these are made up data to prove a point. But you might expect there to be a covariance of the data. So they're going up at the same time, they come down. So if you plot shark attacks against ice cream, it's either that sharks can like the taste of people that are full of ice cream and eat them, or that after having a near miss shark attack, people go in and maybe eat a lot of ice cream to kind of console themselves. Or it could be a third factor that when it's sunny, people go swimming in the water, and when it's sunny, people eat ice cream. So therefore, you have what looks like well, you do have a correlation between the two, but there's no direct causation between them. Okay, so I think that's the end of this. So just go back to that for no reason. So yeah, so correlation we can calculate using let's go back. Calculate using these lovely equations here. This lovely equation, we can calculate how well how much the variance in one variable coincides with variance in another variable. How linear is that relationship? But it doesn't imply anything about causation. Okay, so a little bit of a yeah. So there we go. I'm going to stop soon.